today's presentation is nanomedicine and drug delivery. And I picked this topic because I think without regard of the discipline that you might be starting your path in your bachelor's, at some point you might find it interesting or you might come across with it. So let's get to it. Let me first take a minute to display the traditional territories acknowledgement. And instead of reading it out loud for you, while you read it, I will let you know a little bit more what's my interpretation of it as an international student. I come from a country with a very rich cultural background, and for us in Mexico, it's very common to be living all together with different backgrounds, with different ethnicities. But the thing that as international students we need to be aware of is that the same thing happens here, and it's not only about the multiculturality that we are aware of in our classrooms, but it's also in the foundations of the country. So it's very important to sum up with the efforts to move forward in partnership for the collaboration with indigenous people, of course, but these efforts that we take for the traditional territories acknowledgement, I think they can be translatable also to the relationship that we build with all the other ethnicities that are living together in Canada. So I will let you know a little bit more about myself, my personal background. I graduated from medicine in 2019 from the National Autonomous University of Mexico. After that, I did a research internship in a laboratory of nanotechnology and nanomedicine, also in Mexico. And then after that, I just started in September my master's program here in the University of Manitoba in the Lavu lab. In this laboratory, the main two technologies that we work with are nanomedicine and also organ on chip models, which is also very cool, but I needed to pick one. So I did the reasonable thing to do in these cases, which is to flip a coin. I picked nanomedicine over organs on chip because I think it's more applicable to all the backgrounds that we have present today. So that's the next thing that I would like to know. To make this presentation a little bit more interactive, I will ask you to go to this website, either in your computers or in your mobile phones. You can enter in any device and enter this code or scan the QR code, and then you will be able to answer the questions that we will be posting throughout the presentation. Okay, so I'll give you a moment to enter the Mentimeter, and you will see pretty much every time that we have an interactive activity, these instructions on top. Okay. If you have any questions, please, you can also use the chat at any time. Okay. Then what I would like to know now is, what is your field of study? What's your bachelor's? Let me know a little bit more to see what's the population that we have today. And okay. We have many people from life sciences, I guess. Health sciences, a lot of people, biology, great. Any people from engineering or physics, biochemistry, okay. Something non-related to life sciences, perhaps. That would be interesting. Health policy, okay, that's great. Wow. Very diverse. Cell development, genetics, red and blue. I think those were like trials. Okay. General science. Okay. Health studies, genetics, dental hygiene. You can see that I am excited because for all the fields of study that you can see here in the word cloud, believe it or not, they are nanomedicine applications. So let's get to it. Thank you for sharing your backgrounds. It helps me to know some of the language and to adequate the presentation for the audience. So the objectives for this lecture, sorry, I missed this slide. The content of this lecture is going to be mainly these 6 points. I don't want to give you a lot of information that you can feel a little bit overwhelmed, because the objective of this session is not to make you experts in nanotechnology, but what we will cover is to know what is nanotechnology, general concepts about what is nanotechnology, what is nanomedicine, different types of nanoparticles and what are they used for, some challenges that we encounter in drug delivery when we're working with nanoparticles, and also I will share with you 3 applications that I chose of nanomedicine in targeted drug delivery. And we will have a final challenge that I hope you will find interesting. The objectives for this lecture is to, that by the end of this lecture, we will be able to define core concepts of nanomedicine, also to correlate the types of nanoparticles with the uses that they can have. And the final challenge will, the purpose of the final challenge is for you to propose solutions to a drug delivery problem. Even if you haven't heard of drug delivery before, I'm pretty sure that you will be able to come up with some possibilities. And in the end, I'm hoping that after the lecture, you can reflect on the value of multidisciplinary collaboration and science, okay? So let's start with this gentleman. Let me introduce you to Dr. Richard Feynman. Dr. Richard Feynman was a very talented physicist. He did a lot of very valuable contributions to the field of theoretical physics. But the reason that he's with us today is that in 1959, he was giving a lecture and he said this quote that I'm explaining for you: there's plenty of room at the bottom. So to put this in a little bit of context, think of that year and all the things that were happening by then, okay? Everybody was looking at the sky and trying to figure out how to get to the moon. But when everybody was gazing at the stars, he said, okay, there, instead of looking above, you should look to the bottom. And there is also a lot of empty space that we can exploit, okay? He was referring with this quote to all the space that is between the subatomic nanoparticles. You know, the atoms are composed composed of subatomic nanoparticles, but between the particles are many spaces that can be exploited if we knew how to manipulate them, okay? So these open a whole new field of science that is nanotechnology. The term was not introduced until some years after, but many people consider Richard Feynman the father of nanotechnology. And when people started doing some research of what was happening at the bottom of the matter, they came up with some interesting insights. For example, this stained glass art that is present in one cathedral in France. They found out that the glass staining technique was relying on nanoparticles, mainly some metal nanoparticles like gold nanoparticles, which were given the color red, for example. And these, the people that was doing this glass stain art was around the 1200 year of the current era. So they were using nanotechnology probably without knowing it. But when they started looking further to our ancestors, they found that even in the first years of this era and before, some people were using nanotechnology. So this is a mural from the Mayan culture in Mexico, archaeological site called Punambac. And this very vivid blue staining that you can see in the mural is actually due to copper nanoparticles. So this was not exclusive to the Mayan culture. Also, the indigo blue that you know, it came from India from many years ago. And it's also a pretty much similar principle. So let's get to what is nanotechnology. What is this extraordinary thing that happens between the atoms and in the space between the atoms? Well, nanotechnology can be defined as a multidisciplinary field of science that studies the materials in general when we take them down to the size of the nanoscale. And what size is the nanoscale? The nanoscale is defined from 1 to 100 nanometers, but you will learn from today's lecture that the nanoparticles can have many diverse shapes. So the common consensus is that to be considered a nanoparticle, it should have at least one dimension. If you think of the particle in a three dimension, at least one of the dimensions should be in the nanoscale. Okay, and if you want to know how small is nano, I will put in chat the link that I am showing here, and I will give you a minute to explore it. Okay, I will also put it in the display for you. Okay. So hopefully you can see my screen with the scale of the universe. And this is a very interesting resource because you can explore from the biggest thing that we can know, which is the cosmos, all the way to the smallest thing. So make any stops that you consider necessary. But I wanted to show you from the size of yourselves, all the things that you need to pass only to get to the nanoscale. Okay, so we pass the cells, we pass chromosomes, viruses, and here the viruses you start to see some dimensions in the nanometer scale. Okay, but you need to get all the way to the bottom to find some of the smallest nanoparticles, like the bulkables, which are 1 nanometer diameter. These are nanoparticles that are composed of 60 carbon atoms. And so carbon nanotubes that can be longer than 100 nanometers, obviously, but the cross section of the carbon nanotubes usually is around 1 nanometer too. So this can give you a sense of how small is the nanoscale. Okay, you can explore that resource in detail later. Then getting back to the presentation. Why does it matter? What does the size matter in this case? Well, the answer is implied by the question. Matter has different behavior when you take the things in the nanoscale dimension. Okay, for example, the carbon itself. If you take a piece of charcoal, let's say, and you try to screw it in the light bulb plug, you probably not feel anything because charcoal and carbon in the macro scale is not a good conductor of electricity or heat. But then if you take it to the nanoscale, you'll find that some of the most efficient conductors right now are made out of carbon nanoparticles. Also, for example, some metals that are not magnetic in the macro scale, when you take them to the nanoscale, they can have some magnetic properties and they can induce some electrical fields. So it's very interesting how they behave in the nanoscale. So that's why this nanotechnology field of science has many applications without regard of the field that you are working on. Okay, particularly regarding to nanomedicine. Usually, when you think of interventions in medicine in general, they usually apply either to these three purposes: to prevention, diagnosis, or treatment of a disease or a condition. Okay, so there are many nanomedicine applications that can fit in any of these three purposes. For prevention, we can talk about the vaccines, for example. Probably many of you have had already a vaccine for SARS-CoV-2, which was made out of nanoparticles. But there are also some other purposes as decontamination, some cleaning products, let's say, with nanoparticles that can have antimicrobial properties. And you can even build materials like phone cases or some clothes that have antimicrobial properties by themselves. In the diagnosis of diseases, there are many applications of nanotechnology for imaging in histopathology, which is the analysis of biopsies, for example, from the body. Also some nanosensors that you can implant in the body and measure some vital constants, for example, or concentration of any molecules that you are interested in. And there is a word that you might have heard before, which is diagnostics, which is like some application that can be helpful for the diagnosis, but in the same sense, you can also take advantage of it for the treatment of the disease that you are studying. And getting into treatment, there are many modalities where nanoparticles can be used for, but some of them are photocatalysis, controlled release of drugs, and targeted drug delivery. This means targeted drug delivery to a certain organ or a certain tissue without having the effects of that drug spread all across the body. So the good thing, and as I told before, the reason that I chose nanomedicine as a topic for today is that it's a multidisciplinary field. I would go one step ahead and say that it's interdisciplinary field, and you might ask, okay, what's the difference between multi and inter? As you can see with this Venn diagram, there are many disciplines involved, but the closest that you can approximate the circles is the effect that you can have from the interaction of these different disciplines, right? So if you think of each discipline or each circle separately, you can think of a multidisciplinary approach in which the chemists are doing their thing, the physicists are doing their thing, the physicians are doing their thing, but you only give certain output and you put everything together. Like when we have to do some teamwork or some tasks in the courses, right? But if you move to interdisciplinary fields, then you find out that you might need more closer collaboration with all the other scientists from other disciplines in order to solve the problem that you are trying to address. Okay, so moving forward to the next topic, let's talk about different types of nanoparticles, and I think this is where the interesting thing starts. We're going to talk about different types of nanoparticles based on the material that they are made of. Okay, that's the first disclosure. And this list might not be exhaustive. The thing is that, as you might know, science and research are evolving at a very fast speed. So this is like the consensus and the most digestible classification. Okay. So the first one is solid metal nanoparticles. These nanoparticles are usually made out of metal elements, for example, gold, silver, copper, and these usually have the dense metal cores. Okay, so the cores of these nanoparticles have a high density sometimes, and this allows them to be able to be identified, for example, in imaging. If you do an X-ray and you administer some metal nanoparticles, you might be able to see them whenever you administer it. You can also go further, and if you excite these solid metal nanoparticles with a energy source, once they were administered to a certain tissue or a certain part of the body, you can heat them, let's say. So imagine you deliver these nanoparticles and these nanoparticles arrive to a tumor site, okay, for the treatment of cancer. Then once you corroborated by imaging that the nanoparticles are in the tumor, then you can heat these nanoparticles to destroy the tumor. Isn't that cool? And also, another interesting thing about the solid metal nanoparticles is that they have studied them for antibacterial properties. Particularly silver and copper are very powerful antibacterial compounds. So we will talk more about this application of solid metal nanoparticles ahead in the presentation. Metal oxide nanoparticles are usually made out of, as the name says, combinations of metal oxides such as silicon oxide, titanium, magnesium, zinc oxide, etc. But the main thing is that because the metal ions are linked to some oxygen atoms, they make more spaces. And remember what Richard Feynman said, there's plenty of space at the bottom, right? So you can take advantage of these spaces between the metal oxide monomers, let's say, or particles, and you can load, for example, drugs in these holes, and you can deliver them, and these nanoparticles will release their content in a controlled manner. This might sound like rocket science for you, but actually, probably many of you apply to your skins some metal oxide nanoparticles today after taking a shower, because some cosmetic products like creams, sunscreens, etc., have silicon oxide or titanium oxide, because titanium oxide is usually used as a white colorant because it reflects all the light, most of the light spectrum. So sunscreens usually have either titanium oxide or zinc oxide on them. And also there are other applications such as catalysis, which is like the cleavage of biomolecules. Okay. Then the third type of nanoparticles is carbon nanoparticles. And I said a couple of things before about this kind, and you might find them with some names such as graphene, fullerene, carbon nanotubes, etc. It depends on the shape or the applications that they have. Okay, and some of these applications, as I've said before, are for electrothermal conductivity. So biosensors are also built out of carbon nanoparticles, and believe it or not, these are some of the smallest nanoparticles, but also you can build some of the strongest flexible materials with this. So you can have a sheet of graphene, which is 1 nanometer in thickness, but it can be stronger than some of the materials that we think of when we hear the word strong, such as steel. Okay, and please, if you have any questions or comments about the types of nanoparticles at the moment, let us know in the chat. Okay, let's move to the next ones. There are some nanoparticles also made out of organic polymers, and I'm including here in this category a lot of different nanoparticles. Some of them, most studied ones, are chitosan nanoparticles or dendrimers made out of different organic polymers. But these dendrimers, the main thing is that they are made from branching connections. Okay, so with each branching, as you know, every chemical compound has some structure, three-dimensional structure that they conserve. And when you think of it in a three-dimensional context, all of these holes will be empty spaces that you can also fill with drugs, for example, for drug delivery, or you can even build some scaffolds for tissue engineering. So if you build some fibers, let's say, you can design a matrix for cells to grow in, and this is very helpful for regenerative medicine. Also, chitosan nanoparticles are widely used for fertilizers in agriculture. So these are very interesting nanoparticles too. The next type is quantum dots. Quantum dots are very interesting because the main property that they have is that they can reflect the light in a different wavelength than the wavelength that they receive. So if you excite them, this means that if you excite them with a certain color, let's say, they will reflect another color. Okay. Depending on the size is the color that they reflect. So you can control which color you want your quantum dots to be. And if you think of these as different post-its with different colors, then they will allow you to mark whatever you want with the tags that you can put to them. Okay, the materials that they are made of, mainly the most used are cadmium quantum dots, indium, zinc quantum dots also. But these are also used not only as fluorescent tags, but also as tiny semiconductors for electronic circuits and some nanosensors too. The sixth type that we're going to talk about are viral nanoparticles. And this is some of the best examples of how to use a bad thing for a good purpose. Imagine that you can take a viral particle, you empty the content of it, and you are left with a shell, okay, of the virus. And then you can load the shell of the virus with whatever you want to deliver to a diseased tissue or diseased cell. And then you take advantage of the ability of the virus to infect cells, but they will deliver not the viral content, but the content that you put in. Then there are many kinds of viruses that can be used for these purposes. But to bring an example that you might have heard of recently, some vaccines for SARS-CoV-2 were made out of viral nanoparticles. So they have a lot of applications in immunotherapy, for example, as I said before, vaccines, also as drug nanocarriers, because you can put into these shells, these viral shells, pretty much everything, either drugs or maybe contrast agents for imaging, okay? And the cool thing, and is that the cool thing about quantum dots is when you turn off lights, of course. Look at this difference when you excite different sizes of quantum dots with UV light. It's really mesmerizing. I love that picture. Okay, the last type of nanoparticles is that we will talk about, last but not least, is the lipid-based nanoparticles. And this is probably the most trendy kind of nanoparticles right now, because these nanoparticles are very versatile. This means that you can tailor-make pretty much for the application that you are thinking of. And the advantages of these lipid-based nanoparticles is that they are usually made pretty similar to the biological membranes in all the cells of living organisms. Okay, so if you take a closer look to the image here, you might find familiar that shape is a phospholipid. So actually, the lipids are the filaments that are between the spheres in the image, and the little marbles that you see are the phosphate heads, let's say, of the phospholipids. Okay. The thing to highlight about this is that the heads are usually hydrophilic. This means that they like to be in water, whilst the tails, which are the lipids, are hydrophobic, which is they don't like to be in water, and they repel water. Okay, so taking advantage of these properties of the lipids, you can assemble different types of lipid-based nanoparticles. The one that you are looking at in letter A is a liposome. So it's made out of a double layer, a bilayer of phospholipids, pretty much like all the cell membranes. And you can put any content that you want inside, as long as it's hydrophilic, because as you can see, the inner wall of the liposome is made out of the polar heads, which is the hydrophilic end of the phospholipids. So if your content that you want to load is hydrophilic, you are good. You can use liposomes. If not, then what can you do? Well, you can assemble pretty much any lipid nanoparticles for the purpose that you want. If you want to load hydrophobic, which is molecules that are not soluble in water, in the nanoparticles, then you can use, for example, the letter B, some lipid nanoparticles. Okay, I know the terms might seem confusing, but the important thing about this is that these are only a monolayer of phospholipids. So the inner core of the lipid sphere, of the nanoparticle sphere, the inner medium will be a hydrophobic, and then the outer medium will be hydrophilic. That makes the nanoparticle soluble in water, but you can put any insoluble agent loaded in the middle. Okay, and the little tail that you see here in gray, which are here noted as PEG, that's a coating that you can use to further enhance the compatibility of lipid nanoparticles when you administer them to a living organism, let's say. So as I said before, these are very useful carriers for drug delivery, also for gene therapy, because you can put nucleic acids inside, for example, and you can protect them from being degraded by enzymes or by many other aggressive stimuli, for example, pH, temperature, etc. Okay, vaccines is also a very important application of lipid-based nanoparticles. Do you have any questions about the types of nanoparticles? You can turn on your microphones or comment in the chat. And while you do that, if you have any question, let's move forward to the second activity. So after the explanation of the types of nanoparticles that are presented to you, let us know which one do you think is the coolest, okay? Lipid nanoparticles, fire nanoparticles, quantum dots. I would vote for, okay, I will not bias you. I'll let you know in the end. Great, okay. Okay, we have a question in the chat base. What types of tools can we use to increase the specificity of nanoparticles in the body? Okay, this is a great question. I think I will answer it in more detail some slides ahead in the presentation. But the good thing about the nanoparticles is that they are very, very versatile. So you can attach pretty much whatever you can to the surface. Imagine that you can have an antibody. You can attach an antibody to the surface of the nanoparticle, and you know that antibodies are very, very specific for the protein or the molecule that they are targeting. So you can use this in advantage to target your nanoparticles site, the tissue or the type of cells that you want. Is it possible to directly assemble protein nanoparticles? Yes, it is. Some of the organ polymer nanoparticles can be made out of protein complexes, and you need to think of what properties you want to make them for. But yes, you can. As I say, it's coolest are the quantum dots for me. For me too, because nothing can get over that image when you turn off the lights and turn on the UV. Okay, good. Lipid nanoparticles one. I'm not surprised that that's fair. But second place, quantum dots. Third place, viral nanoparticles. Great. Okay, we have one more question here. What was the PEG for on the outside of the monolayer lipid nanoparticle again? Okay, the PEG is a hydrophilic molecule. Okay, so we said that let me take a step back in the presentation. Actually, I think I will talk about it on one slide ahead. Let me get it. Yes, here it is. I will answer your question. Let's talk about, so we discussed different types of nanoparticles. Let's talk about what are the most determinant properties of nanoparticles to achieve the purpose that you want them to achieve, okay? We discussed the importance of the materials that they are made of, okay? So that's the first one. We can also say that the shape is one of the most determinant properties. I think all the examples that you saw in the images for the types of nanoparticles were spherical nanoparticles, but you can have geometrical nanoparticles too. You can have nanowires, nanotubes. You can have the quantum dots are really spherical, probably. But you can have many different shapes. You can have nanorods, which are like, if you have ever seen rod-like bacteria, yeah, it's like a bean shape. Okay, but the thing is, the shape also influences the response that the body has to the nanoparticles. Okay, the size is also very important, because as the bigger the nanoparticles get, the easier they are to spot by the immune system, for example. And the thing is, you might not want to be in the bigger side, but if you made them too small, then probably the amount of drug that you can load into them is also not as efficient as you would expect, right? The charge of the nanoparticles is also important, because it can determine the interactions with the cells that they are exposed to, and also it affects the things that you can attach to the surface of the nanoparticle, right? So as I said before, you can attach antibodies to the surface, you can attach peptides, you can attach drugs by themselves, and these will affect the the target that you will get for the nanoparticles, right? You can also attach the PEG, which is one of the things that we can also mention in the functionalization of nanoparticles. The PEG coating is usually used to avoid immune recognition by the innate immune system. This means that some of the white blood cells that we have to defend ourselves from microorganisms or foreign bodies that enter to our body, these can also find the nanoparticles, eat them, process them, and get rid of them. So if you coat the nanoparticles with PEG, you usually allow them to be circulating more time in the blood and achieve the target they want to achieve. There's a question here that says, how did you determine a good drug payload? Is it drug over nanoparticle specific? Yeah, the answer is yes. It depends on the purpose that you want. So this question is one of the things that you need to ask yourself when you are trying to come up with a drug formulation. Let's say if you have, let's say, siRNA or a nucleic acid that you know that works to treat certain disease. Okay, now you want to think, how much can I put of this molecule inside the nanoparticles? What size can I make them? What things can I attach them to reach the target, etc. So these determinant properties are some of the considerations, the initial considerations that you need to think of when you are proposing a project. Say. And also, just to mention it, superficial distribution refers not only to the functionalization, but this applies, for example, remember that I told you about the mixed oxide nanoparticles that have a lot of pores on them. So the superficial area in those nanoparticles compared to the volume that they have is huge. So you have a lot of surface in each one of these pores. Think of it as Gruyere cheese, okay? If you were able to spread jam on top of a slice of cheese, if it's plain, then it's only a certain amount of jam you can spread on it, right? But if it has holes in it, then you can put also jam inside of these holes, and it allows you to put more in it. Then if we take this to the chemical interactions of these nanoparticles, it allows for more reactivity of the material. Okay. Okay, and now some of the challenges that we encounter when we are working with drug delivery with nanoparticles. We might have discussed some of this in the previous slide, but one of them is toxicity, obviously, because depending on the material that you are using to build your nanoparticles, you will be probably getting some toxic effects over healthy cells. So these needs to be considered also in the design of the nanoparticles. The stability, because nanoparticles are also sensitive to changes, for example, in pH, temperature, concentrations of ions, etc., depending on the material that it's made of. So you don't want your nanoparticles to break apart, right? The metabolism is also a very, very important challenge because, for example, lipid nanoparticles are usually accumulated in the liver once they are administered to the bloodstream. And you need to think like of a smart way to bypass the liver accumulation. And some strategies that are being used to achieve this effect is coating the nanoparticles with some molecules that give them specific charge. Okay, so if they have, for example, a negative charge, instead of accumulating in the liver, they will accumulate in another organ, to say, as an example again. Immunogenicity, because of course this will be always foreign bodies, even if they are lipid nanoparticles and they are made of the same materials of our cell membranes, they can be recognized as foreign agents, right? The targeting efficiency is usually a concern because obviously you want the greatest amount or the greatest proportion of the nanoparticles to achieve the target that you want, and not to be getting any side effects over other organs or tissues, right? That's what we call off-target effects. And you need to achieve a good balance on the targeting efficiency, but also it's very hard to say that you can achieve a 100% targeting efficiency, because there are many cross-reactivity even with antibodies that can have a very high specificity. You can get some cross-reactivity with other molecules that you don't want to target. Another very cool thing about nanoparticles is that you can even make them by design to be responsive to certain stimuli. For example, pH. You can design your nanoparticles to be activated at certain pH. You can also design them to be activated by certain temperature or by external forces such as magnetic fields, right? So imagine all the things that you can do with all these possibilities. And I added one more here to the challenges of drug delivery with nanoparticles that is not really related to the intrinsic properties of nanoparticles, but also something that you need to think about if you are trying to take a nanoparticle application to the clinical trials, to the market, etc. You need to be aware of. There are many regulatory and ethical affairs that you need to overcome. And the thing is, this is even if nanotechnology started in the previous century, there are still a lot of gray areas when you talk about regulatory and ethical issues. So sometimes you need to propose what would need to be the standards for the assessment of these nanoparticles. So let me know now if you know of any nanomedicine application, if you have heard of recently of any nanomedicine application. Let's see how many can we get. If you haven't, it's totally fine, but let's see if we get some here. No, okay, fair. Vaccines, yeah. Any specific kind of vaccines? COVID-19 adenovirus vector, exactly. So that's a good example of viral nanoparticles. What they did is that they took monkey adenovirus, emptied it, and put some protein from the SARS-CoV-2 to be able to infect the cells and present the protein of the SARS-CoV-2 virus, and then simulate an immunogenic response against the SARS-CoV-2, not against the adenovirus, right? For drugs, okay. For cancer therapy, sure. Cancer medications, there are many cancer medications, well, not many, but a few approved in the market. And you can probably say that some of them were made in Canada. Johnson & Johnson vaccine, yeah, exactly. That's one of the ones that were developed using viral nanoparticles for medical imaging, antibiotic delivery. Wow, you're more familiar with some of them than me, probably. For pacemakers, okay, maybe as electrical circuits, probably. In MRIs for imaging, sure. Implants. Wow, I'm very happy to get all your comments. Okay, let's move forward then. This way that you're familiar with these nanomedicine applications. I will share with you 3 examples that I chose of the most interesting that they seem to me and more exciting. Please be aware that there's only one photo that can be a little bit sensitive to some people. So let's go through this quickly. This is the last section. The first example are copper nanoparticles as treatment for diabetic foot ulcers. What you are looking at here is the design of the nanoparticle and how is it composed of different elements. And these were applied to diabetic foot ulcers, which are some kind of wounds that are very hard to heal. There are some people that have ulcers that never heal, and this can have very serious complications such as amputations. So what you're looking here at is the progress that was made in a chronic ulcer that had many years after they started applying the copper nanoparticles in treatment. It progressed to healing. Okay. Number two, I will just mention this because you're pretty much familiar with this. SARS-CoV-2 vaccine development. Yeah, this article is from 2020. So this was summarizing some of the approaches that can be used for the development of SARS-CoV-2 vaccines. They were using some vaccines with DNA, RNA, some protein subunits, but the common ground of this is that they were enabled by nanoparticle delivery. And also, depending on the design, it's a kind of immune response that you can achieve. So this is very important for the moment that you are establishing your design or your interventions, right? I have a question here from Peace that, oh, you were talking about the ulcers. She says, can this be applied to sickle cell ulcers too? Probably, because it was, what I can tell is that it was also used for chronic pressure ulcers, which are very frequent in people that are laying in bed for long periods, and it worked. And there's another question here: can protein nanoparticle assembly be done with novel amino acids to try and create new proteins with artificially generated amino acids? Oh wow! The answer bar is I don't know, but that sounds very exciting. If you know of it, please let me know. I will be interested in it. I know that aptamers are sometimes used in conjugation with nanoparticles to achieve or targeting efficiencies, for example. But please let me know. And the third example is this. It's just astonishing. If until this moment you were still thinking that nanoparticles were lame, probably this will change your mind. These multi-stage vectors for targeted drug delivery were inspired of how rockets are launched into the space. Okay, as you might know, the rockets are designed with several pieces that start detaching as they progress their way to the orbit. Right. Inspired by that, they designed these devices that have a first stage, which is made out of silicon oxide material. This is actually not a nanoparticle, it's a microparticle because the size is pretty big to be a nanoparticle. But this is loaded in all the small holes. You can load it with the actual nanoparticles that will have the third stage, which is the molecule that will achieve the effect that you want. This has been used, for example, for treatment of cardiac insufficiency to stimulate the muscle cells in the heart to regenerate and to grow again. So this is very exciting.